In this video, I'm going to talk about the PDOS program to generate projected density of states plots. First, what is a PDOS plot? A PDOS plot shows the energy distribution of a chosen subset of electrons in the material. For example, this could be the electrons assigned to a particular atom or group of atoms in the material. A density of states curve is normally for the occupied states, but the program can also plot the energy distribution of the empty density of states. Also, it could refer to electrons of a particular spin, such as spin up or spin down electrons. Also, it could refer to the electrons contributing to a particular soft shell, such as SPDF and or G soft shells. The program can also graph the bond order BO and the sum of bond order SBO curves. A BO curve can be calculated for a pair of atoms, while the SBO curve includes all the bonds to a specific atom. If you already have Python installed in your computer, do not skip ahead, because I want to explain what packages you will need to have installed. If you don't have Python on your computer, go to the Python webpage and download the latest version. Make sure you add Python to the path. Then, open the command prompt and start writing pip install numpy. After done, write pip install matplotlib, which is short for matplotlib library. Nothing bad would happen if you already have those modules installed and type these commands. Here, we use the program to create a PDOS plot for the spin non-polarized boron fluoride. Open the PDOS program Python file. Click the Browse Folder button and we select the desired folder by navigating through the directories. The folder you need to select should have all output files generated by the ChargeMold program. Once found, click Select Folder. Notice that files do not appear in the directory but are in fact there. Make sure you don't forget to click the Run button. The program has default options for the plot options, but you're free to change them. Select the desired units for the plot. Your options are electron volt or Hartree. Then, select the smearing width parameter value. Note that the smearing width only affects the sharpness of the peaks and does not affect the total integral of any curve. For appearance purposes, we recommend using 0.1 eV or its equivalent in Hartrees. Then, select the energy range. This is going to be your x-axis. We recommend -81 to 30 eV or its equivalent in Hartrees. The selection of data points per curve is the number of data points you want to create between the limits set for your x-axis. In this case, there will be 2001 points between -81 and 30 eV, with a uniform increment among them. Then, select how many data curves you want to prepare. After clicking Submit, a new menu is going to appear asking for the atom numbers that you want to create curves for. Notice that the program opens a black window behind. This is the Python interpreter. The program prints some output based on the chosen system. In this case, we can see the element symbol in list form after the atomic underscore symbols tag. Also, you can see the number of the atoms in any of the DDEC output files generated by the ChargeMold program. In this case, I want to explore the fluorine atom in boron fluoride. Then, click Submit Curves and a new window appears. In here, the program wants to know specifically what kind of electrons you want to plot. In this case, I will choose to see the SPDFG electrons. In case you change opinion, you could always click Clear and go back a step. If you don't clear the last panel and only submit with a new selection, you will not have the results you are expecting. So make sure you always clear whenever you change opinion. In this case, I decided to change the last selection to get the bond order DOS in the plot. The new selection consists of drop-down menus to finish your selection. For the first one, I chose the S electrons for fluorine. For the second, I chose the P electrons for fluorine. For the VO, you are going to get a menu with the atom number you selected and other atom it is connected to. In this case, fluorine is the only atom connected to boron. Click Submit. At this point, a CSV file has been generated inside the same folder you selected at the beginning. Now, you could plot your curves and personalize the appearance of the plot by adding title, axis titles, and font sizes. As always, you could change the default values. To start, you may want to look at a graph first before deciding whether to use a secondary y-axis. Choose all primary axes and then write some labels and select some colors for the curves. Click Submit. A new menu appears asking for the graph interval between ticks for the x-axis. The program automatically displays the maximum point for all the curves as the ending point of the y-axis. Next, choose an interval for the y-axis. Click Graph and the PDOS plot will appear on the screen. Notice you can resize the window and move the graph up by selecting this button. Now that I look at the graph, I can see that the black covers the other colors, so maybe I want to move it to a secondary axis. To do that, look at the highest point on the curve you want to move. In this case, is no more than 5 in the y-axis. You could close the graph or keep it open, but you must press clear in the last menu selection. Select secondary for the curve you want to change and click submit. Now the next menu has more options. Select the next axis interval. Now for the starting point of the first axis, you want to shift the axis by -5 units to be able to fit the curve below. Also, you may want to make your ending point bigger to get a better graphic representation. Choose the interval. Now for the secondary axis, you are going to start at 0, but then you need to add the absolute of the starting point to the ending point of y1. In this case, I get 25 and chose an interval for y2. Click graph again, and now you see the BO curve was shifted down and we get a better visualization. Notice you can also adjust the window to your liking by clicking this button. You can adjust the top, bottom, left, and right spaces. Alternatively, you could just maximize the window. I moved the graph up a bit and then I zoomed in on a specific region using the magnifying glass button. Once you think your plot is ready, you can go ahead and save it as a .png image. Now, when I go to the folder, I can see the image and the CSV file, which stands for comma-separated values. Upon opening on a text editor, we can see the values in each row are separated by commas. It is of extreme importance that if you want to continue working on this example and want to go all the way back to the first selection window, you click clear on the first panel of choices, instead of clicking the X button to close the window. Alternatively, you could start the program over. In here, upon clicking the first clear button, the window is closed and now I'm back at the first window. Also, important here, if you want to keep both CSV outputs, you must rename the CSV output previously generated, or else the program will override it. In this example, I will choose to override it. Now I want to analyze the boron atom using 2 curves instead of 3. So I clear the curves and make the selections. The new window appears reflecting the changes I made and continue just as I did last time. I modify the plot to my liking and save the image. Close the program after finished. Now we consider a spin-polarized example of the baryon octacarbonyl molecule. Open the program and navigate to the desired directory. Click Run. Then, update or use the predetermined values for the plot. Choose the desired number of curves and click Submit. In this case, I'm going to analyze the barium atom, one of the oxygens, all of the oxygens, and all the carbons. Please note that if an atom is listed twice for one curve, the atom's population will be included twice in that curve. Click Submit Curves. Notice that with a spin-polarized example, now more options appear on the second window, one for spin up and one for spin down except for the SBO, where you could later select based on spin. For barium, I chose SBO for the oxygen BO and SPDFG spin up populations for the rest of the curves. Upon submission, I make the pertinent selection based on the characteristics I want to analyze and click Submit. Now, I add the title to the graph and notice the tags for the axis changed based on the unit selection. The $sign followed by the underscore makes subscripts. Select primary for preliminary view of the plot and select suitable labels for each curve. Don't forget to pick a color. Select intervals for the X and Y axis and graph the plot. In here, we can see that the colors overlap and all the curves can be visualized. In here, I decided to change the red and blue curves. The highest point of any of them is just below 200. As before, clear the last panel and select the curves to plot on a secondary y-axis. The primary axis needs a shift of -200, and the rest of the numbers are chosen accordingly. Now, the ending point for a secondary axis needs to be 1200. Upon clicking Graph, a new plot appears and the other can be closed not to be confused. Fine-tune the plot and save the image. Here we see the created CSV file with informative headings as to know what your selections for each curve were. In this example, we study the EU C60 endohedral complex, having a net charge of +1. The normal density of states curves are for the occupied states. In addition to the occupied states, the PDOS program can also plot separate curves for the empty, that is, unoccupied density of states. Start the program. Select the folder you want to analyze and run it. If you want to plot the empty density of states, your input files should include data for the virtual, that is, unoccupied orbitals, as well as for the occupied orbitals. Enough virtual orbitals should be included in the input data to cover the energy range you wish to plot. For example, if you want to plot the empty density of states up to energy X max, then your input files have to be prepared to include at least all of the occupied orbitals plus virtual orbitals up to energy X max. Having excess virtual orbitals in the input file does not hurt, because if virtual orbitals above energy X max are included, they will not affect the plot. In this case, I generate 4 curves analyzing the C60 group, which are atoms 1 to 60. In the list of atoms. Submit the curves. I create 2 curves for the SPDFU population and 2 for empty density of states. Since I want to compare the field to empty states, I choose analogous population types for full and empty states. Click Submit and wait a bit for the program to proceed. I will put the full curves on the primary axis and the empty ones on a secondary y-axis. Choose Labels. If desired, you can select the same colors for full and empty states, because the empty states are plotted with a dotted line. Choose a number for the X interval. I choose to shift the Y1 axis by the full amount, as I do not know if that maximum belongs to the empty or occupied orbitals. Choose an interval for Y1 and choose a Y2 ending point accordingly. Upon graphing, we see the empty states could be shifted by less. The difference is around 400 in the Y-axis, so I changed the starting points and ending points for both axes. Now the curves look better. Adjust the plot and save it. In the folder, we now have a PNG image and the generated CSV file. In this example, a PDOS plot was attempted for a CCSD calculation, where the orbital energies are not available. When the folder was selected and the Run button was pressed, an error message appeared on the screen, letting you know that it is impossible to create a PDOS plot for the system selected. When you click OK, the program is going to quit. You can check if your system has available orbital energies in the orbitals_info.txt file, inside the folder where you have the ChargeMol outputs. In here, the orbital energies available tag is set to false, meaning no orbital energies are available. When energies are available, you will normally see them in a list format below. Now that we know how to create PDOS plots using the program, what if we want to generate our own graphs? In this section, you will learn how to create graph templates so that you don't have to separately format each graph you want to create. In this case, I'm going to work with the boron fluoride example. I open the CSV file and save it as an Excel workbook to be able to create and save graphs. Open the newly created Excel file, select the data, and insert a scatter with smooth lines plot. Move the chart to a new Excel sheet. Remove the grid lines by selecting them and pressing the Del button on the keyboard. Add axis titles and remove the title. Select the entire chart area and change the font color to black. Select the x-axis to change where the y-axis crosses the x-axis. In this case, I selected an axis value of -81. Also, change the limits to match the ones set by the data. Choose outside tick labels for the x-axis. Correct the axis titles. Change the font sizes for the axis. Select the y-axis and change the horizontal axis cross to -1 and select outside tick marks. Now change the axis lines to black color and increase the width of the line to 1.5. Change the legend font size. Now, what if you want to have a secondary axis just as in the program? Select the curve you want on the secondary axis and right-click it. Select Format Data Series and select Secondary Axis. Format the secondary axis to match the rest of the chart. To shift your axis, you have to increase the primary axis range as well as the secondary until the curves don't overlap. Since the ranges were changed, it would be good to revisit the horizontal axis cross and move it accordingly. Since you don't want to be making this every time you have some data, you can save this graph as a template by selecting the graph and right-clicking it, followed by the selection Save as Template. Change the name of the template and save it. You can repeat this process to create a template for Hartree in case you want templates for both EV and Hartree energy units. Notice that the first row of every column is the legend displayed on the plot, so you can change it to something meaningful. Let's test our template. Select the data and click Recommended Charts on the Insert panel. Then go to All Charts and select Template. Choose the right template and click OK. Move the chart to a new Excel sheet. As you can see, the data wasn't transferred perfectly, so we need to make some changes. Right-click and click Select Data. In here, we can see that Excel grabbed the comment in the first row and tried to make it into a series. So let's delete that one and edit the rest. In here, it is clear that the X values have not been assigned, so let's select them. Start by selecting the first point for the X-axis and then press Ctrl plus Shift and the down arrow key to select all the data in that column until a blank cell appears, and click OK. Repeat the same for the other curve, and now we have a formatted graph without doing all the editing from scratch. Change the axis titles. Since the template was saved with a secondary y-axis, the data is going to be displayed like that. If you ever want to get rid of it, you can do so by selecting the secondary axis and deleting it. Now our plot has one y-axis. This shows how the same information can be plotted using either two y-axes or a single axis. You can do extra formatting if desired. You have your graphs in Excel ready. After preparing the PDOS plots, how do you put them together and add text labels? I'm going to demonstrate a procedure using PDOS plots prepared in Excel, but you could use a similar procedure to open and copy the PDOS images you saved from the PDOS program. Select the plot section and click Copy. Then open PowerPoint and add a new blank slide. In the Home menu, click the Paste option and select to paste it as a picture. You can then crop the picture to get rid of the borders or resize to your preference. If you want to prepare a stacked PDOS figure, then copy the second PDOS plot and paste it as a picture again in the same slide. Crop it and move it. In this case, the legend and the X-axis title are the same, so I decided to change the order and bring forward the plot that is at the bottom, so it covers the legends from the top plot. In here, notice that the text box can be moved freely by pressing Alt while dragging the text box around. Now you can add as many text boxes or figures as you want to make your plots informative. Since I decided to put a title in the graph, now the curve labels in the legend are redundant, so I go to the Excel file and change them. Select all the objects in the slide and with the right click select to group the content. Now you can save your annotated plots as an image to use it. You should always save the PowerPoint file in case you want to make changes later. The saved PowerPoint file keeps track of the individual elements, so you can add, remove, or edit individual elements without having to start all over from scratch. We would like to thank the NSF Career Award for making this video possible.